Yeah, so I think it's a good time to start the sessions this morning. So right now we already have our speaker, Dr. Zafer Aygin. So he got his PhD from Carleton University, Canada. And yeah, I met him in Singapore when he was a research fellow in 2016 to 2018. And yeah, yesterday I had some discussion with some participants about modular form. So he also write a book related to modular form, and the title is The Applications of Modular Forms. And yeah, it is newly published. So it just published in July 2023 by Springer Nature. And he authored more than 20 papers. So yeah, around 24 international papers. And his research interest is about modular forms, harmonic mass forms, Eisenstein series, Hegel operators, and yeah, related to that. So like rank, and so on. So I think that's all about our speakers, because if I should read all of them, that will be a lot and it will take a lot of time because there are 7 pages here. And the clear thing is, yeah, our speaker for this morning is an expert in number theory, especially related to partition theory, modular form, and yeah, related research topic. So yeah, please for Dr. Zafer Selcuk Aygin, if you want to start your lecture. Thank you.
Thank you for kind introduction, Oha. And it's great to see you again. Thank you for
nice to see
you. Thank you for reaching out, and thanks to organizers for inviting me to introduce my research. So today I'll be talking about n-colored generalized Frobenius partitions. Specifically, I'll talk about generalized Collich's identities. This is a joint work with the results of this talk is a joint work with Nguyen of University of Calgary. So this talk is about 4 parts. Between each part, I want to take a break and ask if you have any questions, so that like that I know the topic is being followed. So it's more like a lecture seminar, between lecture and a seminar, because I'll be skipping lots of technical details too. So not all the details will be given in this talk. So feel free to ask any questions in while I'm talking or in between the parts. So in the first part, I'll introduce what these partitions are about, these n-colored generalized Frobenius partitions. To do that, first we'll talk about Frobenius symbols, then generalized Frobenius symbols, and then finally the n-colored generalized Frobenius partitions. Then we'll look at its generating function, and we will realize that its generating function is related to quadratic forms, and then its associated quadratic form is a modular form. And that's where my expertise kind of comes in, because I have no expertise in n-colored generalized Frobenius partitions. My expertise is in quadratic forms and modular forms. So therefore, we'll apply things we know from modular forms into that quadratic form. And then we will derive 3 important modular identities. And using those modular identities, we'll find a formula for the an asymptotical formula for the n-colored generalized Frobenius partitions. It's a long name, sorry. And finally, we'll discuss, if we have time, we'll discuss how we achieve the asymptotic behavior in our formula. So let's start with partitions. I'm pretty sure You have seen this many times so far, but it's good to review again. A partition of n is a non-decreasing sequence of positive integers that sums up to be n. For example, 4 plus 4 plus 4 plus 2 is a partition of 14. And the number of different partitions of n is denoted by Pn, and we call it the partition function. By definition, we take P0 to be 1 because it makes sense. And for example, if you want to compute P4, you can write the partitions of 4 as 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1. In total, there are 5 of them. Therefore, the partition number of 4 is equal to 5. P4 is equal to 5. So this is the usual partition function. The Frobenius symbols has something to do with the Ferrer's diagram of a partition, like those dots that we do to describe a partition. We can construct a 2 by D matrix by carrying out the following steps. First, we remove all the dots lying on the diagonal of the Ferrer's diagram. And then the first row, in the remaining dots, the number of dots in the first row will be written as the first row, first entry of the matrix. And going down, we will write right next to each other, and it will create the first row of the matrix. The second row is the remaining dots in the columns. So, for example, for the partition 14, 4 plus 4 plus 4 plus 2, the Ferrer diagram is this guy. We remove the diagonals, and then there are 3 elements here. Therefore, the first entry of the matrix will be 3. There is 2, so the next entry will be 2, and the next entry will be 1. And then there are 3 here. So in the second row of the matrix, the first entry will be 3, the second entry will be 2, and there is nothing underneath this, so the third entry will be 0. Therefore, 3, 2, 1, 3, 2, 0 will be the Frobenius symbol for this Ferrer's diagram. So again, 3, 2, 1, 3, 2, 1, and the columns 3, 2, 0, 3, 2, 0. By design, as you see, this must be like the rows here must be a decreasing sequence. But like if you want to generalize this, if you want to let repetitions, then you call it a generalized Frobenius symbol. And any partition that is that arises from a generalized Frobenius symbol is called the generalized Frobenius partition. So formally, we define the generalized Frobenius symbol by allowing at most n repetitions in each row of the Frobenius symbol. For a generalized Frobenius symbol with entries r, I, j, I could be 1 or 2, j is between 1 and d. The generalized Frobenius partition of n is given by this summation. So the number of generalized Frobenius partitions of n is denoted by phi n of n. So, but here there is like the order is a little messed up because you are allowing n repetitions of the same number. If you want to be a little more organized, you can color these repetitions and call this an n-colored generalized Frobenius partition. So it is a little technical. So I'm going to read this definition and give an example. I hope it makes sense. The entries in each row are distinct and are taken from n copies of the non-negative integers distinguished by color. So it's the same thing. You have numbers, you are allowing repetitions, but if there's, you're allowing repetitions, but each number has an assigned color. in each row, the entries are ordered according to the rule that xi is less than yj. So we want to keep them ordered. If x is less than y, if the number itself is less, that means it is less than x is less than y. But if x is equal to y, if the numbers are equal, then we look at their colors. Their colors are also numbered. Their colors also have an order. So if the color I is less than the color J, then we say Xi is less than Yj. So the number of n-colored generalized Frobenius partitions of n is denoted by C phi n of n, and we note that the partition number is equal to the one colored generalized Frobenius partition, because only one repetition is allowed, which there's only one color, which means there's only one repetition is allowed, which means it's the normal usual partitions. So if it is still not making any sense, let me give you an example of a list of two-color generalized Frobenius symbols, which gives rise to the two-color generalized Frobenius partitions of 2. We can write 1, 1. There's a diagonal, so the total number here is 2. So it's a partition of 2. 1 of first color, 0 of second color. 1 of second color, 0 of first color. 1 of second color, 0 of second color. So this is one set. The second kind of permutation, let's say, 0 of the first color, 1 of the first color, 0 of the second color, 1 of the first color, and so on. And finally, we can, like there are two diagonals now, so there are 2 dots for the diagonals, we remove them. So then the remaining elements are zeros. So 0 of second color, 0 of first color, 0 of second color, 0 of first color. We cannot do 0 of first color, 0 of second color, 0 of first color, 0 of second color, because 2 is greater than 1. So that's how ordering works in these colored generalized Frobenius partitions. So if you count these, there are 9 of them, which means C phi 2 of 2 is equal to 9. So now, in 1991, by the way, these are defined by George Andrews in his memoir. I think it was 1985. And 1991, college has come up with 3 equalities, which relates the n-colored Frobenius partitions to usual partitions. So he proves that C phi of 5 of n is equal to 5 times partitions of 5n minus 1 plus partitions of n over 5. Here, if n over 5 is not an integer, we take this to be 0. And if n over 7 is not an integer, we take this to be 0, and so on. And this applies to any arithmetic function we see today. So these kind of relations exist for only 5, 7, and 11. At least that was the only ones that were known. And these are usually called Collins identities. In 2019, Chen, Wang, and Yang. Is Wang there? I saw his name among the speakers. Okay, so yeah, so they have proven, they have generalized this to all primes. But as you see, there is a leftover term if you want to do this for all primes. So for 13, when there are 13 colors, C phi 13 of n is equal to 13 times p of 13 n minus 7 plus p of n over 13 plus a leftover term, where the leftover term is given in terms of this infinite product. If you are not familiar with this notation, I'm going to give the definitions later on. For now, just know that these are infinite products. That's all. And an is the nth coefficient of Fourier series expansion of this infinite product. And if p is greater than or equal to 17 and is a prime, then the same expression here has another leftover term where hpz is a modular function on gamma naught p with a 0 at infinity and a pole of order this at 0. In their paper, this hpz is also given explicitly. So this is a very nice extension of the Kollitz identities to all primes. So what comes next? Usually when someone does something for all primes, the next thing is square-free integers. So we got curious about what's going on, and we tried what happens if we take the colors to be a square-free positive integer. And as usual with these partition theory things, we take the G's, we take n to be co-prime to 6. So n is a square-free number without the primes 2 or 3. So if this is the case, the same thing happens, like the results of Chen, Wang, and Yang is almost the same, except that this part is now runs through all divisors of n rather than just divisors of p. And there's a leftover term here again. And therefore, we can write C phi of n in terms of a partition function and a leftover term, even when n is a square-free positive integer. Here, this C of z, here Bn is the Fourier coefficient here, where Cz is a cusp form in this modular form space. So, okay, now, if this Bn is equal to 0, we can get like Kollitz type equalities, right? So we got curious, when does this happen? So apparently it never happens again. It happens only when n is equal to 5, 7, or 11. In all other cases, this Bn, actually this Cz is equal to 0. So we can't get an exact formula in cases other than 5, 7, or 11. Okay, now, it doesn't happen all the time, but does it start to happen? Like, is this Bn equal to 0 for sufficiently large n? That's also not the case. So unless n is equal to 5, 7, or 11, there is no m such that Bn is equal to 0 for all n greater than m. So basically, Kollitz identities are the only identities that can give exact formula for C phi of n in terms of the partition function. Okay, now that's a bummer, right? We can't find exact formulas. Now, next question. Is this leftover term, what's the size of this leftover term compared to this guy? Apparently, it's very small, and we were able to prove that they're asymptotically equal for n large enough. So all in all, as n goes to infinity, C phi n of n is similar to this linear combination of partition numbers. So this is This is kind of nice. Now we know how C phi of n is related to partition functions for square-free numbers. Now, as I mentioned before, to be able to do this, we need to work with the generating function of the n-colored Frobenius partitions. We denote the generating function by the capital C, capital phi, n, q, and this is going to be our generating function. Andrews, in his memoir in 1985, he determined this generating function in terms of a theta function. The theta function we use is theta n, where the xi squares are taken from 1 to n, and each copy of xi times xj, except when I is equal to j. So this is like, this has a very nice matrix, we will see soon. So this is a quadratic form in n variables, and we denote fqnz to be the generating function of number of representations of integers by this quadratic form. So f theta n z is equal to q theta n x, where x is in integers. So this is its associated theta function. With this notation, the generating function of n-colored generalized Frobenius partitions is f theta. Be careful here, this is not n, this is n minus 1 over the infinite product of 1 minus q to the power n to the power n. So now, this is the key point here. Now I know this function. I can work with this function because it's a theta function. It's a modular form in certain cases. So it's good to work with. I like those kind of functions. So before I go to part 2, I want to take a few minutes break and ask if you have any questions.
Any question? Okay. They still try to understand the whole thing. So we can, I think we can continue.
We can continue? Okay.
Yeah.
Give me a second. Now, okay. Let's talk about, now we have established that there is a quadratic form here, which we can deal with, but how? Now let's talk about quadratic forms and their relation to modular forms. First of all, if theta is a positive definite quadratic form in 2k variables, then the associated theta function is a modular form in mk gamma naught n chi d, where n is the smallest positive integer such that the matrix n times q to the power -1 has even diagonal entries, where q denotes the matrix associated with theta, and this character is -1 to the power k s if s is odd and it satisfies this congruence property, and in all other cases it's -1 to the power k times 4 times s, where s denotes the square-free part of the determinant of q. So in order to determine the modularity of a theta function, we first need its associated matrix. Then we need the determinant of that matrix and the inverse of that matrix. Luckily, all of these are done by Chen, Wang, and Yang in the 2019 paper. So the matrix associated with theta n-1 is an n-1 by n-1 matrix with diagonal entries 2 and all other entries 1. Remember, we had one copy for each xi, xj. So That is what that means. And these 2's are for the diagonal entries, meaning xi squares. And for a technical reason, we must multiply those by 2. So that's how we obtain this matrix. And they additionally calculate that the determinant of Q is equal to n. This is the matrix associated with n minus 1. So its determinant is n. And the inverse of that is 1 over n times n minus 1 minus 1 all the way. And diagonals are n minus 1, and all other entries are minus 1. So this is great, because now we can determine the space these theta function belongs to. If n is a actually in this paper they have proven this for all numbers, but I just need the part where n is a square free integer with GCD and 6 is equal to 1. Then we have f theta n minus 1 z is in this modular form space, where the character is given by chi of n, which is the Kontrakan symbol, minus 1 to the power n minus 1 over 2 n over a, meaning if n is congruent to 1 modulo 4, this is plus 1, meaning this is n over a. If n is congruent to 3 modulo 4, then this is negative n over a. It's because we want this to be quadratic discriminant, and that's why we need these plus or minus signs. But other than that, this is a Kontrakan symbol. So now we know that this is a modular form, but we don't know what modular forms are yet. So next, I'm going to define what modular forms are and try to explain a few things about them, and then we'll see how we can get our modular identities. So first of all, the modular subgroup of level n is defined by gamma naught n, where this A, B, C, D, R is a matrix with integer entries, where C is congruent to 0 modulo. This should have been a capital N, and its determinant is equal to 1. So it's a subgroup of SL2Z, where this C is congruent to 0 modulo capital N. Now, let k be a positive integer and chi be a Dirichlet character modulo n, where chi minus 1 is equal to minus 1 to the power k. If this is not satisfied, then the modular form is going to be trivial. So we are putting this just to make sure that we are not dealing with a trivial modular form space. Then we denote the space of modular forms of weight k and character chi on gamma naught n by mk gamma naught n chi. So, I mean, you've probably seen the definition of modular forms quite a few times, but as a refresher, a modular form is a function that satisfies a certain transformation property, and on its cusps, it's holomorphic on the upper half plane, and it's holomorphic at each cusp. So this has a very nice how to say projection onto Eisenstein series. So we can write MK as a direct sum of Eisenstein series and cusp forms, where the cusp forms are modular forms that vanish at cusps. So the significance of this direct sum property is as follows. Because of this, if f of z is a modular form whose Fourier series expansion is given by AFN q to the power n, then there are unique functions in Eisenstein series component of the direct sum, whose coefficients are EF of n, and cusp form component of the direct sum, where we denote the coefficients by CF of n, such that this the coefficient of the modular form is the Eisenstein coefficients plus the cusp coefficients, and this representation is unique. And one other thing is that by Hecke bound, we know that the size of C of n is big O of n to the power k over 2. And this is the crucial thing for us. Now, we claimed that our formula was asymptotical, right? So this is why our formula is asymptotical. In our case, this Eisenstein part is much bigger than n to the power k over 2. Therefore, this leftover part is going to vanish when n goes to infinity. Like it's going to be insignificant when n goes to infinity. So that's why this direct sum representation is very important. But how do we get this direct sum representation? To be able to do that, first, we need to find... Okay, before I move forward, I have to emphasize that we do not actually need to know we do not need to know an explicit formula for CF of n, because it's going to vanish when n goes to infinity. So we are only interested in an explicit formula for this part. Okay, let's move on. Now, in order to find an explicit formula for that part, we need to give a basis for the Eisenstein space. So this E of n will be given explicitly in terms of generalized divisor functions defined by sigma k epsilon psi n, where we take this finite sum over the divisors of n, epsilon n over d, psi bar d to the power k, if n is an positive integer. If n is not a positive integer, we take it to be 0. Here, epsilon denotes a primitive Dirichlet character of conductor L, and psi denotes a primitive Dirichlet character of conductor M. So, for example, if n is odd, then we have sigma k, chi minus 4, chi 1. These are the same Kronecker symbols from before. 2 to the power j times n is equal to, because of its infinite product, because of its multiplicative properties, we can separate sigma k 2 to the power j times sigma k n. So here is the part that's associated with 2 to the power j. This is the other part. And then if you look at this carefully, this is 2 to the power j over d, where d divides 2 to the power j, chi minus 4. So this is a Dirichlet character of conductor 4. Therefore, when this is an even number, when it is not coprime to 2, this is always going to be 0, which means this is always 0 unless d is equal to 2 to the power j. Therefore, the only term that survives here is 2 to the power j to the power k. And the rest is here. So this example is important to understand something that's going to happen in the upcoming discussions. So in certain cases, we can actually extract this to be just a coefficient, and it's going to come handy when we are working on our formulas. So again, if this guy and this guy are not coprime, then you can extract the non-coprime part as a constant. Okay, moving on, we define the Eisenstein series, which will help us to write a basis for the Eisenstein part of a modular form. We define the weight k Eisenstein series associated with epsilon and psi. Epsilon and psi are the same as before, by ek z epsilon psi equals to epsilon 0 minus 2k over bk chi, where this is Bernoulli number associated with the Dirichlet character chi, and sigma k minus 1 epsilon psi n e to the power 2 pi I n z. So this is the Eisenstein, classical Eisenstein series. Yeah, anyways, I'm just gonna move on. I mean, usually in the books, the modular form books start with the Eisenstein series, where there's epsilon and psi is equal to chi1, chi1. This is just a generalization of that Eisenstein series. So nothing extraordinary is going on here. But for us, this is significant because the space ek gamma naught n chi admits a natural basis of weight k Eisenstein series, which is described below. Now, when k is greater than or equal to 2 and k and chi is not 2 and the identity character, the primitive principal character, the collection of all Eisenstein series where epsilon psi is equal to chi gives you a basis for the space. So basically, we are taking all possible Eisenstein series in the space, and that forms a basis for this guy. And remember that we excluded this case in this one. If this is the case, then it's a little different because we need to be careful about the modularity of certain Eisenstein series that are coming from the characters chi1, chi1. It's just a technical detail, which is not important because it's not going to change anything. So therefore, we know that we can write the Eisenstein part of any modular form as a linear combination of these Eisenstein series. And that linear combination is explicitly given in one of my previous papers, which was published in 2022. It's called Projections of Modular Forms on Eisenstein series. So for any modular form, we have the EF, the Eisenstein part of F, is given by this linear combination of Eisenstein series, where AF is explicitly given in terms of the constant coefficient of the modular form. So all these functions are very nice. If you just put in the numbers, it will return you the numbers. Before moving on, I have to discuss what this is, what the constant coefficient of a modular form is. So if A is a integer and C is a non-zero, C is a non-negative integer, which are co-prime, then we denote the constant term of f of z in the Fourier expansion of f of z at the cusp A over C by limit cz plus d to the power minus k f of az plus b over cz plus d when z goes to I infinity, where b and d are some integers such that a, b, c, d is in SL2z, and the value of this constant coefficient are independent of the choice of b and d. So whatever you choose, you'll get the same result. Therefore, in the notation, we do not include B and D. So this is, by computing this limit, we can find the constant coefficient of any modular form. Which means that this theorem is quite applicable, and we will apply, we will specialize this theorem to our cases and then work with the resulting modular identities. So remember, our functions were in another, in a special modular form space. So that modular form space was m(n-1/2) gamma naught n chi n, where n is a square-free integer with GCD n6 is equal to 1. In that case, if we specialize the previous theorem, we get this result. So the Eisenstein part of f, there should have been an e here. There is a typo there. F of, oh no, actually no, we include the constant part, so this is correct. So it's given in terms of the constant coefficient of f, and the rest are just some arithmetic functions, which are very nice. And if we can compute the constant terms of our functions, then we'll be able to give the modular identities. So, okay, now let's roll back a little and remind you what our goal was. Our goal was to find 3 modular identities, which will help us to give the n-colored generalized Frobenius partition in terms of the usual normal partition function. So this theorem is going to help us to give those modular identities. So this finishes the second part of my talk. Are there any questions?
Maybe we give some time for participants if you have any question. Because I think some of us is not really familiar with cast form, and when it appears, how to deal with them. Maybe you can.
Right. So for our purposes, that cusp forms are not really important. So just it's a special kind of modular form. We'll not be working with cusp forms. They're going to go to 0 when n goes to infinity. Does it make sense?
Yes.
Okay. That's why I didn't, I mean, these are too technical. If I go into the details of everything, it's gonna take a while.
Actually, we had SIMPA school also 2020, and we discussed also about the modular form. So yeah, but yeah, again, I think for a lot of mathematicians, especially for students, it's not, it's still challenging for us to fully understand the whole thing about the modular form.
Right. Okay. How do? So it is like modular forms are very nice functions, right?
Yep.
So
correct.
So if you think of them very nice people, then maybe it becomes more accessible. I mean, first of all, we know lots of things about modular forms. We have this direct sum representation of them, which allows us to write formulas, asymptotic formulas. Actually, let me go back. Actually, this is a very nice question. Thank you. So here, when you write a modular form in terms of Eisenstein series plus a cusp form, then you actually, most of the time, you obtain a asymptotical formula. Because as I mentioned, by Hecke bound, this is big O of n to the power k over 2. And usually, this part is n to the power k minus 1. The size of this part is n to the power k minus 1. Therefore, you obtain an asymptotical formula for like if you have something which is a modular form or related to modular forms, then it's quite easy to get an asymptotical formula. To be able to do that, you have to write the Eisenstein part first, and then play with the where is it? The sum of divisors function. So it's usually quite fruitful. I mean, I hope it's making sense.
Yes. Maybe any more questions? I think if you have any difficulties in speaking in English, so you also can speak in Bahasa Indonesia, and then I can help you to translate. Just in case you want to ask, but you feel how to ask.
Yeah, there's no need to be shy or
right.
feel like your question is stupid or something, because like these are not easy things. So if you have any question, I would appreciate.
Okay, I think, yeah. At least yesterday we have learned together from Liu Chen for some the application. So at least I think they can follow some parts that how to use the modular form, and this part should be okay for us. So I
Okay.
can go. Okay.
Great. Very nice. Okay, so let me have some water and I'll keep on.
Yes. Please.
So, okay, now we'll create our modular identities, the identities that we are going to use to prove our formulas. So, first of all, I mentioned that we need to compute the constant terms of the theta functions. Sorry, the function of interest. In this case, we are interested in this theta function. So its constant term is actually a Gauss sum. So if you take that limit and play with around with the terms, you get a Gauss sum, expression which is related to Gauss sums. So this is the this is not a Kronecker symbol, by the way. This is the imaginary I over D to the power this guy. So here we have a Gauss sum divided by square root of capital N, where this Gauss sum is defined by this exponential sum. So Gauss sums are a challenging subject. There's lots of things known and there's lots of things that are unknown. Like, for example, if our theta function was a diagonal form, then computation of this Gauss sum would be very easy. But in our case, it is not a diagonal form. You have seen the associated matrix. It's like diagonals were 2 and the rest of the entries were 1, 1, 1, 1. Therefore, like, this is a very challenging computation. It's very technical. I'll try to explain what we did to compute this just by giving the headlines. I don't think I can go into the details. But first of all, they have a very nice multiplicative property. So if alpha, beta, and gamma is mutually co-prime, then G of n gamma alpha times beta is equal to G of n beta times gamma alpha G of n alpha gamma times beta. So this is specific to the Gauss sum associated with the quadratic form we are working with. So with that one, we have this nice multiplicative property. By exploiting this like a million times, we obtain recursion for GNAP, which is given here. Here, when n is equal to p minus 1 or p, the formula is nice. But if n is greater than p, then it becomes a recursion. And this formula, we obtain this formula by exploiting the previous multiplicative property and the usual Gauss sums. And then by using that recursion, we obtain that g of n minus 1 AP is equal to I to the power this guy, A over P times P to the power n over 2. And then finally, by using the multiplicative properties and moving things around, for any that divides n, we have g of n minus 1 AD is equal to A over D times I to the power. This A over D is a Kronecker symbol, by the way, so it's plus or minus 1. I to the power this guy times D to the power n over 2. And then if we put this into the original formula, we obtain the first term of the theta function we are interested in at 1 over D. So it's given by this expression, which is quite simple, actually. So putting this into the projection formula, we get our first modular identity. Remember, okay, I guess I should have been more clear here. So remember, our formula was this, right? Now we have computed the constant term. So we put that term here, and then like just play with these terms, move them around and do some cancellations. And as a result, we get this our first modular identity. So this theta function is 1 plus this constant times this, I mean, these are all constants, times this sigma function, this sum of divisors function, where C3 is some cusp form, which we don't really need to know. It can stay as an arbitrary cusp form. And this constant is either plus or minus 1. So this constant here is plus or minus 1, depending on D and N. And when we put things together, this is not going to matter either. So, but it has a nice representation in terms of Kronecker symbols. So this is our first modular identity. Next, now we want to what's it called? Sorry. Okay, it's here. So we want to associate these functions with the partition function. To do that, we will use eta quotients. So have you seen eta quotients before? Have anyone mentioned them in these talks?
Wilson has mentioned it, and also
okay, perfect. Then that's good, but I'll go over it again. We use eta quotients to relate n-colored Frobenius partitions with the regular partition. It's because of this. Before the technical details, let me tell you why I'm using eta quotients. I'm using eta quotients because the generating function of the partition function can be given in terms of eta quotient and Dedekin's eta function. So this is why we are using the eta quotients. Okay. So the Dedekin eta function, eta z, is a holomorphic function defined on the upper half plane and is defined by infinite product of e to the power 2 pi I n z, where n goes from 1 to infinity, multiplied by e to the power pi I z over 12. In terms of the usual q notation, this is q to the power 1 over 24 times 1 minus q to the power n. N goes from 1 to infinity. Or if you prefer using this usual q series symbol, it is q sub infinity times q to the power 1 over 24. The quotients of products of eta dz for integers d in the form eta RD, DZ, where RD can be any integer, and this multiplication runs through divisors of n, are called eta quotients of level capital N. So we are using eta functions because the partition function can be written in terms of the eta, Dedekind's eta function. But this function by itself is not a modular form. Is not in our space at all. So a version of this is eta to the power n over d times z over eta dz. So if we study these eta quotients, we figure that they are modular forms in the space we are interested in. So this eta quotient and the original theta function we were working on are in the same modular space, which means there is a hope to write them as linear combinations of each other. So if functions are in the same modular form space, then it's a good thing. Then we can actually relate them to each other in a linear way. Okay, now again, we will take advantage of the projection formula we have just seen to create a modular identity using these eta quotients. To be able to do that, we need to know the constant coefficients of these eta quotients. So if C is a divisor of n, then the constant coefficient of this eta quotient is given by these terms here if C is equal to D and 0 otherwise. So D is here, D is the divisor of n, C is the divisor of n. If C is equal to D, then it's non-zero and it's 0 otherwise. So again, we put this into our function and move the terms around and obtain this modular identity. So eta to the power n over dz, eta dz is equal to these terms. So now I'd like to get your attention to this sigma function here. If you have a very strong memory, you'll notice that this is the same sigma function that were used in the previous modular identity. But this is not related to partition functions yet, okay? So in order to relate this to the partition function, we first, we apply a Hecke operator to both sides of this modular equation. The Hecke operator we are applying is this which isolates the coefficients that are divisible by the coefficients of q to the power n, where n is divisible by m, and then shrinks them. So it only takes the coefficients that are multiples of m and shrinks them to the power q to the power n. So this is the operator that we are using. Recall that the partition function was given in terms of the eta quotient. So if we apply the Hecke operator un over d to the left-hand side of the previous modular identity, which was this function, we obtain now the n over d, the coefficient of n over d in this function is q sub infinity. So to the power n stays the same. And then the n over d coefficient of this, because of this, is a partition function. And then after shrinking, we have to divide everything by n over d. And the formula inside the partition function becomes this. So this is kind of like after a few change of variables, we get this expression on the right hand, on the left hand side of the previous modular identity. And then we apply the same Hecke operator to the right-hand side of the previous modular identity. Remember that I told you that if n is divisible by n over d, then there is a way to remove that n over d as a constant coefficient, right? That's going to come in handy here. Because of that, the expression here is not going to change, except that n over d will become a coefficient now. And therefore, we will have our third modular identity, which is a sigma function related to a partition function. And the key point in our result is actually figuring out how to use this Hecke operator. This was this was the key point. Before realizing this, we were only able to associate the n-colored generalized Frobenius partitions to sigma functions. But after realizing this Hecke operator, we have been able to relate it to the partition functions. So there's lots of tricks that you can apply when modular forms are involved. So once we do this, once we obtain this third modular identity, recall that our first modular identity was this guy. Now, I wish there was a way to put them side by side, but I'm going to go back and forth, and you will notice lots of similarities. First of all, this sigma function is this sigma function here. This coefficient here is the same coefficient here. This coefficient here is very similar. It is here, except that, actually, yes, we have already removed n over d. So this actually is equal to this guy, right? So see, all these terms correspond to these terms here. So if we replace these terms with these terms in the next expression, all of these guys will be in terms of the partition function plus some cusp forms. So putting them together, we obtain that C of phi n of n is equal to n over d times this partition function plus some leftover terms, where this leftover terms times this function is a cusp form in this modular form space. And then remember that this CZ is equal to 0 if and only if n is 5, 7, or 11. And if n is not 5 or 7 or 11, then there is no m such that the n is equal to 0 for all n greater than m. There you go. So once we combine these modular identities, we get our first expression. So now this is straightforward, the proof of the first identity. We just write f theta z in terms of the partition function, and then we divide both sides of this equation by q to the power n. Then remember, the generating function of this was f over q to the power n. Therefore, the left-hand side becomes the partition function, right-hand side becomes free of q sub infinity to the power n. Therefore, we have this nice formula. And then once we compare the coefficients of qn in this formula, we obtain the first part of our results. The second part is kind of straightforward by doing some calculations. So first of all, when n is greater than or equal to 29, a square-free positive integer coprime to 6, and if d is less than n, a divisor of n, then this number is always less than or equal to 0. Which means that this p to the p of some negative number, which is obviously 0. So this part is going to be 0 when n is greater than or equal to 29. And we know that C phi of n1 is equal to n squared. Therefore, b of 1 becomes n squared, which is non-zero. Hence, when n is greater than or equal to 29, a square-free positive integer that's co-prime to 6, C of z cannot be 0 because there is at least one non-zero term. Now, similarly, this settles the theorem for numbers that are greater than or equal to 29. What happens if we have n is equal to 13, 17, 19, or 23? In these cases, we have b of 1 is equal to this guy. And then if you calculate this, you obtain 26 when n is equal to 13, 170 when n is equal to 17, and these numbers, which are clearly non-zero. Therefore, in these cases, C of z is not equal to 0. Therefore, by Collit's identities, C of z is equal to 0 if and only if n is equal to 5, 7, or 11. So this is straightforward. Now, the next part is a little technical. It requires properties of modular forms. So in order to prove that part, we prove it by contradiction. Now, assume that there is an m that's greater than or equal to 0, such that Bn is equal to 0 for all n greater than m. Then we would have this leftover part is equal to Bn q to the power n, n goes to from 1 to infinity. But since Bn is equal to 0 by assumption for n greater than m, this will turn out to be a finite sum. Basically, since this is a meromorphic modular function, it satisfies a transformation property. These kind of like finite exponential sums cannot satisfy a transformation property, which gives a contradiction. Therefore, this guy must be it gives a contradiction. So unless n is equal to 5, 7, or 11, we do not have any m such that Bn is equal to 0 for all n greater than m. So there is always a leftover part, is my point. So any questions before I move forward to the asymptotic behavior?
Okay. So,
sir, I want
okay.
to
Yep.
before you already said that about quadratic sum.
Can you hear her voice?
I couldn't hear it clearly. Can you repeat?
Minta.
Quadratic sum. Can you decide the quadratic sum?
So this one.
I want to know that the a power 2p, is that a character function or not?
Yeah, this is a quadratic form. Yeah, it's a quadratic function.
Character function or not, sir?
So I cannot hear clearly.
I want to know that that is all of 2p I a theta m x over c is character function or not, sir?
Is it a character function?
Is it a character function?
Yeah, that you know after, yes.
Oh yeah, this theta.
I.
Oh, this I is the imaginary.
No, I mean from the natural number, and the power, and the power. I'm sorry, my English is not very good.
Yang sebelah mana?
Maksudnya 20 kuadrat itu. Pangkat 2B itu. Nah, itu.
This one?
I mean, E O power 2B I A theta n x. See, is it a character function or not, sir?
So the whole thing E power.
Honestly, I can't hear you clearly. You're asking if it is a certain type of function, but I can't catch what type of function.
Character function. As we know, Z.
Oh yes, this is a theta function. Yes, this is a theta function. This is the, yeah, this is this function here. Let me go back. So that theta n is this theta n.
Yes, but I mean the E power 2 I A theta n x over C, is it a character function or not, sir? As we know, Z modulo C, Z power n is finite group, finite abelian group. Is it?
Yeah, it's basically we are taking the sum of all x. Like this is.
Yes.
Yeah. So this n is actually like n copies of the numbers modulo C. So this x is like x1, x2, x3 up to xn, right? So we run through all xi, all xi runs through all modulo classes over C.
Maybe can we go back to the Dirichlet character?
Dirichlet character, sure.
Yeah. I think it should be clear if we start from there.
This one? I mean, the problem is I can't really hear.
Yes, I mean the chi symbol.
Right. This is a quadratic character. Yes.
Yeah.
Oh yes. Okay. Thank you, sir.
Okay.
The microphone keeps cutting. That's why I couldn't hear.
Okay.
Yeah. Your
Because
microphone worked well.
di situ aja. Saya pakai ini aja. So can you hear me? Maybe.
Yeah. I can hear you well.
Because using several microphones, so the participant also can ask directly.
Right. Okay.
Yeah.
Sorry. Yeah. That's why I couldn't hear the question correctly. Sorry about that. Any other questions?
Yes. Okay. Any other question? Maybe can you share with us, because when we look at the eta function, actually it is not directly related to partitions, and then when we apply the Hacker operator to certain modular function, and then we can find the relation. Maybe you can share in general, because the generative function for certain partition maybe is more complicated. So how is the idea to make a relation between some modular function to, yeah, maybe the general idea.
Okay, well, here's the thing, lots of trial and error. So in modular forms, you have certain tools. So you keep on trying, like if one of those tools work, then you stay with it.
Correct. Yes.
So basically, we lost our way so many times, and like we finally found the right way to approach the question. So it's lots of trial and error. Like if I see another problem, like there's no set rules on what to use for all questions.
Yes, because this morning we have a discussion in number theory. Sometimes we try a strategy, maybe it doesn't work, and try another strategy. Oh, it works, and sometimes it is difficult to explain why is it works.
In this case, why it works is clear because it relates it relates the sigma function to partition functions in a nice way, where I mean, the appearance of this term is actually quite crucial here. Like, I mean, whichever Hecke operator you apply to this, you will always end up with a partition function here. But this term may not be as nice as this one.
Yes. Yeah. That's it. Because sometimes we also modify the operator also to get some.
Yeah. There are other Hecke operators too.
Yes,
I mean,
correct.
probably it is wrong to call this a Hecke operator, anyways. But I'll call it a Hecke operator.
Okay. Yeah.
Yeah. There are more generalized operators that you can apply. The good thing about those operators is they keep the space the same. I mean, they're close within the space.
Same space, yeah.
Yeah. So, that's one of the tools. But I mean, you can't believe how many things we have tried to approach this question. Anyways.
Okay, so go back to trial and error. But yeah, for this case, I think it should be clear the reason why using the operator.
Yeah. For the I mean, okay, here actually this discussion is good. So here, when we are applying this theorem, another thing is to be able to compute these constant terms, right?
Yep.
This is also a very complicated computation, and like for each function, this computation of this changes. Luckily, for eta quotients, where was it? For eta quotients, it's well known, and like you have all the terms that you need. You just combine them and find it. So for the eta quotients, that computation is quite straightforward. So if you have a generating function which can be written in terms of eta quotients, then applications of these becomes much easier. Or if you have a theta function, a diagonal theta function, it is much easier. In this case, for example, we had a non-diagonal theta function. Let me show you. Yeah, this theta function is not diagonal, meaning it's not a diagonal matrix. Therefore, the computation of Gauss sum, meaning the computation of the first term of the associated theta function, was not straightforward at all. We had to come up with novel arguments.
That's it.
Yeah. So
okay, thank you very much.
So one straightforward way to use modular forms.
Yeah. Okay. Any more question? Maybe. I think that's all. Maybe.
Okay. Just give me a second.
Okay.
Now, I'll briefly discuss how we determine the asymptotic behavior. I've already told you, gave you the headlines of why the asymptotic behavior works the way we want. But like if you are interested in the headlines of what we have done, is we just fixed the sigma function part of the generating function to be u of n. Now, if we look at the size of u of n by using the properties of those sum of divisor functions, we find that u of n is much bigger than n to the power n minus 3 over 2 if n is greater than 5. And if n is equal to 5, u of n is much greater than n over log of n. So remember, when I told you about the Eisenstein part and the cusp part. I told you that the cusp part was of size big O of n to the power k over 2, right? K in this case is n minus 1 over 2. Therefore, the contribution from the cusp part is n minus 1 over 4. If n is greater than 5, n minus 3 over 2 is much bigger than n minus 1 over 4. So this is basically the contribution from the Eisenstein part. So we just play with these terms and extract as many coefficients as we can from here, and then put them in a nice form and show that its size is greater than this guy. And when n is equal to 5, it's a little different, but almost the same. And we obtain that these terms are greater, much greater than n over log of n. And then we define VRFN to be the Fourier series expansion of this guy, where this is the generating function for the partition function. So the R power of this is like R convolutions of the partition function. And if you look at the sizes of this, you'll see that VR of n over VR of n minus 1 is kind of like the same size. So this limit goes to 1. And VR minus 1 over VR n is equal to 0. This is going to be handy. So when n is equal to 5, 7, or 11, there's actually nothing to prove because the formula is an exact formula. So it's naturally a asymptotical formula. But if n is not equal to 5, 7, or 11, meaning if we assume n to be greater than 11, by a modular identity from before, we have that this guy is a cusp form. So f theta n minus 1, z minus 1 minus the Eisenstein part. So basically, modular form minus its Eisenstein part is a cusp form. This is a trivial statement. And using the Hecke bound, this cusp form is of size n to the power n minus 1 over 4. By this third modular identity we have determined, the identity minus its Eisenstein part is clearly going to be a cusp form. Therefore, by using Hecke bound, we obtain that this partition function minus the Eisenstein part is also big O of n to the power n minus 1 over 4. Now, with this notation, we have C phi n of n minus this guy is equal to big O of this guy, and this partition function minus this guy is equal to big O of this guy. So if we are looking for the ratio of the C phi n of n and the linear combination of the partition functions, we are actually looking at the ratio of these guys. And here, this to obtain the desired result, we must show that these are the main terms. Okay, if these are the main terms, meaning if this is much smaller than both of these guys, then this limit will go to 1. So to show that, we show that this guy is the Liddell law of this guy as n goes to infinity. I mean, the proof of this relies on the previous arguments we have done. So the previous statement I have shown you, this Eisenstein part being much bigger than L to the power n minus 3 over 2, which dominates this guy. This gets a little technical afterwards. I mean, this is not the proof, but the idea is here, which proves that if n is a square-free positive integer that's co-prime to 6, then the size of n-colored generalized Frobenius partition is similar to this linear combination of the partition functions. So this is all I wanted to talk about today. I hope it made sense, and if you have any questions, it's welcome.
Okay, let's give him a big applause. Okay, so it is the last chance to ask if you have still have any question, because I know some of you are doing research on related to this kind of stuff also, but not closely related, but still doing some stuff they are using this kind of function. Because again, as mentioned by Dr. Zafer Selcuk Aygin, that modular form is really a nice thing that a lot of nice properties also, and we are using a lot, and the application is the expert for the application of modular form.
So really, if you have any questions after the talk, this is my email address. You can always email me, or if you are curious about how to apply these things, I will try my best to answer your questions. So it's very welcome.
Yep. Okay. Last chance. Who want to ask? If you anybody, I check the chat box. I think no one asking. So I think it should be enough. So we can thank you very much again for sharing with us today in this session. And let's give him one more big applause. Thank you very much, and maybe see you. Hopefully, I can see you again.
Sure, yeah. I'll try to stick around for the next few sessions, but it's too late here. It's hard to
yes.
But I'll be around for a few more hours.
I think if you want to leave, that's also fine, because I know you are busy.
No, don't
it's
worry
up
about
to
it.
You.
Thanks a lot for the invitation.
Thank you very
Thanks
much.
for listening to what I had to say. Have a
Bye.
great. Bye-bye.